Hi guys, in the last videos we saw the DMA and we configured through the thing and we saw that data path to the FIFO, from the FIFO and read back. The whole time the DMA was working, the zinc waited for the DMA to finish. This means that the zinc cannot do anything until the DMA finishes. Now sometimes the packages are very long, so instead of using polling like in our old design, we want to do now interrupt. In the interrupt mode, the data path is the same. Once the zinc started the DMA is independent and the zinc can go on its business until the DMA finishes the transaction, and then it generates an interrupt. The interrupt stops the zinc go back to the DMA, process it, whatever it needs, and go on with its program. We will also do the design in simulation. So for simulation we cannot simulate the zinc, so we're using the Microblaze CPU, which is a soft core from Xilinx, and we will load the same program from the zinc into the Microblaze. We'll do some changes to fit it to the Microblaze. We'll see all the transaction in simulation, so we can see it slowly, and then we will run it as well on the zinc like it should be. We will start with our old design from a DMA1 video, and in this video we will run the code in simulation. To run the code in simulation we need the Microblaze. We add the Microblaze, run connection automation, give it 32 Ks of RAM and no cache, and we'll auto connect it to the DMA through the peripherals, so we have the connection between the Microblaze and the peripheral. Now the Microblaze doesn't have an interrupt controller, so we'll add an interrupt controller. We'll connect it to the Microblaze. We'll run connection automation to connect it to the Microblaze through the interconnect. And since the DMA has two interrupts ports, we'll add a concat combine the two DMA interrupts, connect its output to the interrupt controller, and we'll enable the zinc interrupt port and connect it here as well. Now the Microblaze, in the simulation we cannot see the DDR from the zinc, so we need to have another memory. We'll add a VRAM controller. Now this memory should be seen by the DMA and by the Microblaze, so we'll add a new port to the Smart Connect, one more slave port and one more master port. The master port will be connected to the VRAM controller, and the slave port will open another master port in our interconnect, and now we have a path from our VRAM controller through the Smart Connect, through the interconnect to the Microblaze, so we can write directly to the VRAM controller. We'll add the VRAM and we'll connect the clocks, and we need to assign the addresses. For that, we go to the microblaze space addresses and we assign the VRAM, and we need more than 8 Ks. We need 120 Ks for our software, and we assign the same software to the DMA. Here. One more thing we need now is the microblaze doesn't have a UART, and we cannot use UART in simulation because it will take too long and it will be difficult to read. So we'll add a GPIO and we connect the GPIO itself to the RGB LEDs, so we'll have 6 bits, and we'll connect the GPIO AXI port to the microblaze through the interconnect, and we have our design ready. After we finish the design, we generate block design, and we'll export the hardware. I'll go to the software and remove the old software from the previous videos, and I will extract. We don't have a bit stream yet, so we'll use pre-synthesis bit stream. We'll direct it to our software folder, and now we're ready to start on the software. We'll go to Tools, we'll launch Vitis. We'll direct it to our software directory, and we'll create an application project. We next did the XSA. We'll go again to our software project folder, and we'll take the XSA. Next, microblaze inter software. We are using the microblaze. We'll use the application. And we'll import the example design like we did in the first video, going to the Vivado installation, Vitis installation, version, data, embedded software, Xilinx processor lives, drivers, the last driver of the xaxidma, examples. And in the old video we used the polling example, now we'll use the interrupt example. Now we can start on the software. Now, if we look at the software, it's very similar to the software that we used on the polling. We still have to configure the DMA, we still have to initialize it, check if it's scatter gather, and move on if it's not. But here we have set up interrupts. This is a special function I will discuss a little bit later. Disable and enable the interrupts for the DMA, and starting the loop, configure the RX buffer, configure the TX buffer, and let the DMA run. Now here we are waiting for the interrupt. Now we check the TX done, the RX done, and the error. Now the TX done and the RX done and the error are global variables. They are initialized in the main function, and the handlers change them to indicate that the handler ran. Then, like before, we have the check data and finish the program. Now we need some changes. Now that we have, instead of the DDR, we have a BRAM, and the BRAM is assigned to address C000. So we change the memory base address to C0000. Now we have a smaller memory than we have in the DDR, so we'll use smaller size for the data. The next thing we need here, we don't need 100 length. In simulation it will take very long, so we use only 20. We don't need 10 transfers, we only need 1. And we want to replace the printfs with the GPIO. So we go to the X parameters, open declaration, and look at the GPIO. And this is the its base address. We'll define here a U32 pointer, we'll call it GPIO, for this address. Now this will be our indication where we are in the program. Next, we'll remove all the printfs. So the printfs, we cannot use them, so we will replace them we'll remark them. This has to be done with care because some of those lines are 2 lines and we have to make sure they are all gone. So this is 1 line, this is 1 line, this is 1 line, this is 1 line, and here are 3 lines, so we have to remove everything. And that's it. Save this. Now we want to mark the software so we can see it in simulation. We'll use the GPIO parameter. In the beginning, we will indicate GPIO 0 equals 0, 1. Now we configure the DMA, we initialize the DMA, we check the DMA, and we check for scatter gather. That's not important. Here we're going for the interrupt initializations. So we mark this as well. Here it is. And we'll mark this with 8. Next, we'll mark the enable disable and the variables. Now we'll mark the data initialization and the loop. Here is the loop, and we'll mark again the wait and coming out of the wait state. And the check data we'll write here. We'll mark it at 30. And just to see, since everything here was a printf and we don't have anything yet, we will use the GPIO again to print what was read from the memory received. And once it's done, one more thing we need to mark. This is the handlers. The handlers, this one will mark as 21 and coming out of the handler. (22) and the RX buffer (23) and 24. That's it. Our software is ready. Let's compile it. And into software we have debug port. Here is our source code, and here is the ELF file which we need for the simulation. So we go back to the simulation, to the design, and assigned ELF file, go to our software directory, debug ELF file, and our software is in our design, ready to be simulated. We still need a test bench. Now the test bench is very simple because everything is done inside the block design, so we only have to instantiate the block design. So we'll add a source, a simulation source, create file, DMA test bench, We don't need inputs or outputs, it's a simulation. We'll mark this as top level, and we remove the inputs and outputs, instantiate and we'll take out also the GPIO bus, so we'll have something in our test bench, so it won't be empty. Don't really need it, but it's helpful. And that's it. And now everything is ready for the simulation, but this video has turned out to be very long, so this I will do in my next video. Thank you.